This is the strange case of the Umbral Calculus. Now, if you've never heard about Umbral Calculus, don't worry. It's a piece of 19th century math that evolved into a completely different area in modern mathematics. But I'm not here to talk about the modern version of Umbral Calculus, I'm here to talk about the old school version of it. Because quite frankly, it's really, really weird math, which automatically makes it really, really interesting. To give an idea of what old school means here, it was created in 1862 by this guy, John Blizzard. Now, as it happens a lot of things in mathematics, the creator sometimes doesn't get the credit, but instead it goes to the people using it the most, in this case, Edouard Lucas and James Sylvester. As you may have guessed from its name, it comes from umbra, the darkest part of a shadow, and it has nothing to do with actual calculus. Instead, it's actually a toolbox of algebraic manipulations that really, really deserve its shadowy, shady name. In fact, if I were the one naming this, I would have named something like shifty or magical calculus instead of umbral calculus, because it really is like magic. It makes no sense, but still, it works. Now, the best way to show how umbral calculus works is with examples. And as with any magic trick, it gets much better with a story behind it. So suppose you're studying for your finals in college, and of course, you kept going on until very late at night. You're half asleep already when you move on to the next problem in your book about mathematical induction. It's something to do about proving something involving sequences, and you start writing it down, but you're already so tired that you end up mixing up the indices and the exponents, an expression that you need to prove. Look at it, think about it for a while, and just go, oh, it's just a binomial theorem. So we have b equal to a plus 1, so a equals b minus 1. So if we take the nth power, that's it. Easy. You feel like you're about to black out, so you decide to call it a night. In the next morning, you go back to what you were writing last night and you pick up your mistake. Still, that coincidence makes you decide to at least check some cases, just in case that it's not a mistake in the book or something like that. The idea of the problem that's actually written in the book is that you have some sequence A, and from this sequence A, you build sequence B, and then sequence B and A are related according to the relation that you should have proven. So let's check this out. Let's start with a sequence A. We'll use A0 equal to 2, A1 equal to 1, A2 equal to 0, and A3 equal to 3. Now, following the instructions of the exercise, the sequence B should be defined like this. B0 will just be A0, which is 2. B1 will be A1 plus A0, which is 2 plus 1, that's 3. B2 is going to be A2 plus 2A1 plus A0, which is 0 plus 2 times 1 plus 2, which altogether gives 4. And B3 is going to be A3 plus 3A2 plus 3A1 plus A0, which is going to be 2 plus 3 times 1 plus 3 times 0 plus 3, which altogether gives us 8. Now, if the exercise is correct, then starting from the sequence B and defining sequence A according to the relation that you should have proven should lead you to the sequence you started with. So let's check that. Our sequence B is B0 equal to 2, B1 equal to 3, and B2 equal to 4, B3 equal to 8. Now, following the instructions, A0 should be B0, which is 2, which is what we started with. A1 should be B1 minus B0, which is 3 minus 2, which is 1, also what you started with. A2 should be B2 minus 2B1 plus B0, which should be 4 minus 2 times 3 plus 2, which is 0, also what you started with. And the same thing happens with A3. If you put everything together, you get 3, which is the number you started with. So the exercise seems to be written right in the book, at least this example you built checks out. So maybe we got lucky with this example. Let's try then doing this completely algebraically instead of thinking of a particular sequence A. B0 is just going to be A0. A1 is going to be B1 minus B0, and since we know what B1 and B0 are, we can see that all the parts that are not A1 simplify, and in the end we get A1. A2 should be B2 minus 2B1 plus B0. Once again, substitute all the things we know about B, and we see that everything cancels out except A2. And the same thing happens for A3, even though it's a bit more complicated. Everything that's not A3 cancels out. Before trying to redo the exercise the right way, you decide to try something else first. You got to this coincidence by considering that B equals A plus 1, which is equivalent to A equals B minus 1, taking the nth power on both sides and then mixing up indices and exponents. So you wonder, what would happen if I had started instead with B equals A plus 2? In this case, you can think of two tests that you could do. You know that this would imply that A equals B minus 2, and also that A plus 1 equals B minus 1. So let's check if taking the nth power on both sides of these expressions and then mixing up exponents and indices still gives us something that checks out in the end. Let's start with the situation A equals B minus 2. Now, from the binomial theorem, we know that B equals A plus 2 means that B to the nth power equals this, while A equals B minus 2 means that A to the nth power equals this. So if we mix up exponents and indices in the same way that we did when we were solving our exercise, we should get this relation. So let's define B. B0 is going to be A0, B1 is going to be A1 plus 2A0, B2 is going to be A2 plus 4A1 plus 4A0, and B3 is going to be A3 plus 6A2 plus 12A1 plus 8A0. And we get something very similar for A. Now, what we need to do to check that this is actually true is that these two ways of defining B and A are consistent with each other. So if we substitute one in the other, we should get an equality. So we substitute B0 in the expression for A0, B1 and B0 in the expression for A1, B2, B1, and B0 in the expression for A2, B3, B2, B1, and B0 in the expression for A3. And just as before, everything cancels out and we get the right results in the end. So maybe this is not a coincidence. Maybe there's something deeper here. Let's try A plus 1 equals B minus 1. Let's do the same thing. Take the nth power, expand it using the binomial theorem, then mix up exponents and indices. B equals A plus 2 still means the same thing for us, and A plus 1 equals to B minus 1 will mean that A and B are related according to this equation. We mix up exponents and indices once again and get to the conclusion that this is now the relation that should hold, which is now considerably more complicated than the ones that we tested already. So maybe this one will break. We do the same thing. We define B and we check the relation. We should have that A0 is equal to B0, A1 plus A0 equals B1 minus B0, A2 plus 2A1 plus A0 must equal B2 minus 2B1 plus B0, and A3 plus 3A2 plus 3A1 plus A0 must equal B3 minus 3B2 plus 3B1 minus B0. We substitute everything, and to our astonishment, it works. It still works. What we just did by mixing up exponents and indices in a way such that relations still hold is the main idea behind Umbral Calculus. Before moving on to the details, let's see how the exercise in your book should have actually been solved. We have that Bn is defined by this, and we want to show that this combination of the b's equals A of n. Now we can substitute the definition of bk in this expression to get this. We then rearrange the sums so that the sum over Q is the outermost one. And what we need to show is that this equals AN for every sequence A. And the only way that this is true is if this combination of binomial coefficients is 0 when n is different than q and equal to 1 if n equals q. Proving this relation between binomial coefficients is the part where mathematical induction would come into play. But the proof is a bit long to do right here, so I'll just link to it in the description. Also, this same relation between binomial coefficients is the thing that is behind all the other examples that we did so far. One thing that becomes very clear here is that the correct proof is actually much more complicated than this proof that we found using Umbral Calculus, even though this simpler proof is complete nonsense. So, is this it? Is Umbral Calculus just a coincidence specific to this case? Well, not really, because that same idea of mixing up exponents and indices pops up in a lot of different places, and it was particularly popular for the study of numerical properties of some sequences, like the Bernoulli numbers and the Euler numbers. But isn't mixing up exponents and indices just nonsense? Why does it keep working? Well, it didn't always work, but it certainly did work more often than it should. However, it took a while until someone decided to dig deeper on why all these coincidences happen. The first mathematician to give it a go was Eric Temple Bell in the 1930s. And his approach is what he called the Umbral Algebra between sequences. His idea was the following. We can represent sequences by letters, A, B. So A represents the sequence with terms A0, A1, A2, A3, etc. Same thing for B. B represents the sequence B0, B1, B2, and B3. A and B are what he called umbral variables. And these variables obeyed a very particular algebra. It is that you can define an umbral addition so that A plus B represents a new sequence, such that the nth term of this sequence is this sum that mixes up the terms of A and the terms of B using binomial coefficients. We can also define an umbral multiplication that is just the multiplication of the terms in the sequence A and B put together. And another thing is that you can use numbers as umbral variables too. So if you have a constant C, you can think of this constant C as representing a sequence where the nth term is the nth power of C. So for example, the number 2 would represent the sequence 1, 2, 4, 8, 16, etc. Written in this language, our original problem becomes showing that if B is the umbral addition between A and 1, this means that A is the umbral addition between B and minus 1. And his idea was that if you prove properties of these umbral additions and umbral multiplications, then using these properties, you could manipulate these umbral variables and get to expressions that were very, very similar to what happened in the usual Umbral calculus. However, there were a lot of drawbacks to this approach. For starters, it was limited to simple cases. A second point is that this feels more like a description than an explanation. What I mean by this is that what you're actually doing here in this Umbral algebra is that you're proving properties of these umbral operations. But the point is that you're proving these umbral relations in the same way that you would prove in a rigorous way the old umbral relations too, just like what we did with the correct solution of our exercise. And what can be seen as the final nail on the coffin is that the algebra is counterintuitive, especially once you start mixing up the same umbral variable. For example, the umbral addition between A and A is different from the umbral multiplication between 2 and A, which is not something that you would expect. A much more satisfying solution would still need to wait 40 more years. In the 1970s, over 100 years after the creation of Umbral Calculus, Giancarlo Rota and Stephen Broman showed that what was happening, all of those crazy nonsense calculations that everyone was doing in the 19th century, were deep down nothing more than linear algebra. But the point is that it's linear algebra written with a horrible notation. So let's give it a closer look. The point is that you can think of the Umbral variables that Bell used as representing polynomials instead of representing sequences. And you can think that Umbral expressions have a hidden linear operator acting on them. Let's look at an example to make it clearer what this means. Suppose L is a linear operator acting on polynomials. And it is defined in such a way that if we apply L to the nth power of x, the result is going to be the nth term of some sequence A. If we do this and we apply L to the nth power of x plus 1, then we can use the binomial theorem and then the linearity of L to rearrange things. And finally, we can use the definition of L to find out what the result is going to be. Now, if we recall, this is exactly the way that we define our sequence B in our exercise. So what we have is that L applied to the nth power of x plus 1 is the nth term of sequence B. But the point is that now we can use this new relation to turn things around. Check this out. We know that an is L applied to the nth power of x. And we know that x is just x plus 1 minus 1. So we can rearrange things this way. We once again use the binomial theorem, and once again we use the linearity of L. But now we're going to use the fact that L applied on the nth power of x plus 1 equals the nth term of sequence B. And once we do this, we get exactly the result that we wanted to prove in our exercise. And note that this is pretty much the proof that we did using Umbral Calculus, which is way, way simpler than the quote-unquote correct proof using mathematical induction. Now, what we did gives an explanation of why Umbral Calculus works without having to actually prove anything new. We're just using properties of linear algebra to explain why the algebraic manipulations that we did back then actually make some sense. You're just omitting the operator L everywhere when you do the old school Umbral Calculus. Now, this might leave you with an impression that just like Bell's formulation of Umbral Calculus, this linear algebra formulation is also only able to deal with the simpler cases of the old school Umbral Calculus, but that's not really the case. If you recall, one of the use cases that the old school Umbral Calculus had was studying the numerical properties of some numerical sequences, like the Bernoulli numbers. The way this was done was like this. We know that the function x divided by exponential of x minus 1 has the following Taylor expansion, where the bk are the Bernoulli numbers. Now the trick here is that you can mix up the index in b with an exponent in b and call this an exponential of bx, where here b would kind of be the Umbral variable in Bell's formulation. So the exponential of minus bx would be the exponential of b times minus x, which should be the result of substituting minus x to the expression where that equals exponential of b of x, which leads to this. But we can now rearrange this and get exponential of x times the expression represented by exponential of b of x that we can rewrite like exponential of b plus 1 times x. This must hold for all x's, so obviously this means that b plus 1 equals minus b. Now, remember, these are Umbral variables, so this does not mean that b is minus 1/2. What this means is that if I take the nth power on both sides, expand everything using the binomial theorem, and once again mix up exponents with indexes, I should get this relation, which actually works, as crazy as this sounds. Now, I really expect that you should be confused by this thing, because the rules that we're using here are kind of arbitrary, actually. We're just using rules because we know these rules work, but none of the rules actually make sense. So let's try using this linear operator L to see what's actually happening here. In a similar way as we did in the first example with the linear algebra formulation, we'll define L in such a way that if we apply L to the nth power of the variable b, the result will be the nth Bernoulli number. This shows you exactly what is the role of the operator L. It is the operator that does the quote-unquote mixing up exponents and indices. So what would happen if I applied L to the exponential of b of x? Well, we use here the Taylor expansion of the exponential, use the linearity of L, and then use the definition of L to find that it is now the Taylor expansion using the Bernoulli numbers, which equals x divided by the exponential of x minus 1. So the Umbral expression we just found actually means that applying L to the exponential of bx will give us x divided by exponential of x minus 1. In a similar way, if we apply L to the exponential of minus bx, the result is going to be L applied to the exponential of bx times the exponential of x. We just need to redo the part that actually made sense in our previous Umbral calculation. Now, since L acts only on b, we can bring the exponential of x inside of the operator, and we can actually rearrange the exponential in the way that we did when we were doing the old school Umbral calculus. Now, if we do the Taylor expansions of everything and use the linearity of L, we end up with this relation. And now, since these two Taylor expansions must be equal, they must have the same coefficients, which means that L applied to the kth power of b times the kth power of minus 1 equals L applied to the kth power of b plus 1. Just to connect all the formulations here, this Umbral expression is in the linear algebra formulation. The form of this expression using Bell's Umbral algebra would be that the Umbral multiplication of minus 1 with b is equal to the Umbral addition between b and 1, which is actually what we mean by minus b equals b plus 1 in the old school formulation of Umbral calculus. One thing that's really, really nice about the linear algebra formulation is that it also explains the situations when the old school Umbral calculus breaks up, which is something that Bell's formulation really, really struggles with. For example, if we consider 2x divided by exponential of 2x minus 1, this should be exponential of b times 2x using the old school notation. And then we are tempted to say, well, this should be the square of exponential of bx. And I know what the exponential of bx is. So these two functions should be the same. But if we look at the graph, we can see that they really, really aren't. And there is no reason why, in this specific instance, Umbral calculus does not work. At least, not at first sight. If we, however, use the linear algebra formulation, we know that what we actually mean by exponential of 2bx when we equal this to 2x divided by exponential of 2x minus 1 is that L applied to the exponential of 2bx equals 2x divided by exponential of 2x minus 1. Whereas x squared divided by exponential of x minus 1 squared is actually the square of what we get if we apply L on the exponential of b of x. And now, since L is a linear operator, there is no reason why we should be able to move the square outside of that, because that's not something that linear operators normally do. So it's not an operation that you would think that you can do. So from this point of view, it's very, very clear why these operations don't work. Well, that's all for this video. Thanks for watching and have a nice day.